Okay, so in this video, I'm just going to go over the paper one, 2023 past external exam from QCAA physics. Obviously, I'm not I haven't like revised fully. Now, this is part of my revision, kind of. Yeah, it is. So expect there to be some mistakes, but obviously we will be going through the answers right after doing each question because I'll be using exam insights. Also, just um, for your information, I'm new to OBS. I'm not very familiar with the software, so bear that in mind. Um, I have set up two scenes, so I've kind of figured out what these are. So what I can do is I can switch between showing my screen, so screen sharing, and also showing what's here. So I'm using a iPhone SE 2020 for the camera to demonstrate my working out. I have a graphics calculator with me. Obviously, it's not mandatory. You could use a scientific calculator, but I think in terms of the actual external exam, it's probably more beneficial for me, or just, yeah, for anyone, to use a graphics calculator because it does save the calculations for you. So you can refer back to them once you've completed it, or hopefully completed the question. Okay, well, that's enough chatting. Yeah, let's get around to it. Obviously, I'll also try my best to go fast, right? Prioritize time, but also uh, try my best to explain my thought process for each question. Again, we're only going through paper one. Maybe in another video I'll go through paper two. Okay, an object is unable to accelerate to the speed of light because length contraction will change the height of the object. Doesn't really have relevance to the statement. Time dilation will decrease the velocity of the object. That's not really the main reason. The object will gain infinite momentum. Yeah, that sounds about right. The inertia of the object will decrease. Again, that would probably allow it, that would probably support it in accelerating to the speed of light, you know? So let's see. Okay. Photons are gauge bosons that exhibit wave characteristics. Yeah, that sounds about right. But we'll have to go through the other options. They're not leptons. They're not mediators of the weak force. Mediators of the weak force are W bosons and Z bosons. Particles that can only travel in a medium? No, they don't require a medium to travel through. So it's A. A current carrying wire is shown. Okay, so here, good thing about exam insights is that you can access the formula sheet, like just in the application. So for this question, we're given current and we're given some distance. It's not the length of the wire, so it's not capital L. So up here, these are the formulas that we need to refer back to. Okay, we're not dealing with the solenoid, so it wouldn't be this formula here. Again, we're not dealing with, we're not given the length of the wire, and we're not trying to work out the force. We're trying to work out the magnetic field strength, which is capital B. So if we don't have the force, and we don't have the length of the wire, we don't have beta because it's not even inside an external magnetic field, that formula is not relevant. So it must be this formula up here. E equals mu naught I over 2 pi r. Let's say you didn't know what that constant was. You can go to the back of the definition and access the constants. So we get magnetic constant, which is 4 pi times 10 to the negative 7. Okay. So current is 0.5 amps and the R is 2 centimeters. We need to convert that to meters. So I actually tried this question earlier, but it's very simple anyway. Okay, so we'll write down the formula. We don't have to, because it's a multiple choice question. You're going to be awarded marks for doing that. We should also sum the values. So 0.5 amps for current. R was 2 centimeters. If we convert that to meters, it's 0.02. Okay, so now we can cancel out 4 pi with 2 pi, leaving us with 2 in the numerator. 2 times 0.5 is 1, so we can just kind of scribble those out. Obviously, working up here is getting pretty messy. Having 0.02 in the denominator basically means it's like you're dividing it by 1 over 50. And if you're dividing it by a fraction, you just flip it. You get the reciprocal of it. So overall, it becomes 50 times 10 to the negative 7, which becomes 5 times 10 to the negative 6. So that's one part. So that's one part of the question. So based on the calculation, it's either A or B. But it specifies whether it's out of the page or into the page. So now we can use our right-hand rule. So here, if you didn't know, the right-hand rule is basically you just do kind of like a thumbs up, and that's basically it. You know, the thumb represents the magnetic field. No, it doesn't. It represents current. I meant to say current. Okay, so it represents the current, the direction of the current, and then the other fingers are the direction of the magnetic field. Now, when we do a thumbs up, we kind of curl our fingers inward, and that's exactly what happens here. So since our thumb represents the current and current is going downwards, we aim our thumb downwards, our fingers curl like this, so they're going kind of clockwise. In my perspective, it might be the opposite from the camera's perspective and your perspective. It's curling around like that. So X is over here, and at X, my fingers are pointing towards me. So they're going out of the page. So it would be A. Kepler's third law. I wouldn't say I'm extremely confident in Kepler's laws of planetary motion, but I do know Kepler's third law is on the formula sheet. It's the t squared over r cubed equals 4 pi squared over gm. Gm kind of gives a hint as to what formulas are used to derive Kepler's third law. So we know Kepler's third law is it doesn't describe the elliptical orbit of planets. I think that's its first law. Combines Newton's first law of motion with uniform circular motion. I don't think that's true. Equates the area of the arc sweep of a planet to the time taken to complete it. I think that's the second law. That's the second law. So it's D. And it makes sense because the law of universal gravitation, I believe, is just ink. It's here. I believe so. This is equated with this, I believe. So when one of the masses cancel, we sub in 2 pi r over t for v. Yep. And then that gives something. I don't really remember. Yeah. Okay. It is D, I'm pretty sure. Yeah, it is. Young's double slit experiment. Okay, before we even um, see what the options are, we know that Young's double slit experiment kind of supports the wave model of light because of the diffraction, in the and interference, the destructive and constructive interference, which is just from the dark and light bands that are observed in on the other side of the double slits. Okay. Light behaves differently in different frames of reference. That relates to special relativity, but not as an experiment. Shares characteristics with mechanical waves. It does share characteristics with waves, yeah. It is a longitudinal wave. It can be a wave, or it shares characteristics of waves and particles, but it's not just solely a wave or solely a particle. So it can't be C or D. It's B. Yep. Okay. Question 6. An object of mass 6 times 10 to the 2, so it's just 600 kilograms, travels along a path as shown. The object takes 25 seconds to complete the semicircular section of the path. Okay, so immediately we should be thinking uniform circular motion. And also that hint is given because it says calculate the centripetal force. Immediately we should be relating, centripetal force, we need to go to the formula sheet, or if you've memorized the formula, it's F equals mv squared over r. We know what r is because we're given the diameter, which is the distance from y to z, and we can halve the diameter. So halving 160 meters would give us 80 meters, and meters is the SI unit, so we don't need to convert it to a different unit. That's the exact value. Then we're given the mass, which is 600 kilograms. Kilograms again, SI unit. We don't need to proceed with any conversions. V, we need to calculate V. We are given time, but is this the period? No. The reason why is because it takes 25 seconds to complete the semicircular section. So it's half a circle. So if we presume that it's a full circle, it would take double, right? Assuming that it has an average velocity, or average speed in this case. So what we do is just let's write the values down. So R equals 80 meters, mass equals 600 kilograms. Whoa, my bad. Technical difficulties. Okay. T, which is the period, is actually 50 seconds because I'll tell why. Well, I think I told you earlier. I think I explained it earlier. Since it takes 25 seconds to travel half a circle, which is a semicircle, and since centripetal or uniform circular motion has a constant speed, it will take double the time to travel double the distance. So all the values that we need. Okay, so V equals 2 R over T. What is that? We can just sub it in. Yeah, we can do that, but after we put into the calculator. So 2 pi times the radius, which is 80, divided by the period, which is 50. We don't need to write it down. It's sub it into the centripetal force, formula. It's mass times velocity squared. So we're going to use that. Then we're going to square the entire bracket. We're going to divide it again by the radius. So we get 758 newtons. It's not focusing, but I promise you it's 750. Okay. 758, if you round it to two significant figures, which is what the answers are in, it becomes 7.6. Set speed. An electron and positron can annihilate into a photon, producing another electron and positron pair in the process. The outcome of this interaction is that pure baryons will be produced. Total mass decreases. No, the mass would just stay the same. Conservation of mass and energy, you know. Fewer baryons will be produced. Well, there are no baryons involved in this interaction. There's only leptons. The lepton number does not change. It doesn't change. Yeah. So let's see. Incident light with a frequency of... Okay, so this is relating to photoelectric effect. Incident light with a frequency of 1.7 times 10 to the 15 hertz is shone onto a metal surface with a work function of... Okay, so the units are all in SI units. Frequency is in hertz. Work function is in joules. Determine the kinetic energy of a photoelectron ejected from the metal surface. Okay. Just write the values down before I change the screen. Okay. Okay, so it's just the kinetic energy. So if we have a frequency of 1.7 times 10 to the 15, and we have a function of 10 to the negative 18, I believe. Just double check. Yeah. And these are one SI units, so that's 4. Okay. So we use our formula to get that. So the maximum kinetic energy of the photoelectron equals HF minus the work function. So it equals 6.626. So H is our part. So it's 6.626 times 10 to the negative 44 on formula sheet. To be honest, there's no point in writing this down. Yeah, I won't write it down. I'll just demonstrate it on the calculator. Okay. Because you don't get awarded marks for writing the value down, like there's no point. Okay. So we multiply it by 2, and subtract that to the right function. So it's very okay. Going closer is actually worse. Wow, that's 6.626. So hopefully you can read that. Times 10 to the negative 34 times 1.7 times 10 to the 15 minus 10 to the negative 18. That gives us a value of 1.2642 times 10 to the negative 19. Okay. So when rounded to two significant figs, it's 1.3 times 10 to the negative. Ooh, this question is pretty good. Okay, I'll change the screen one more time just to control this. It's technically one of the answers. It's incorrect because it's in the wrong units. All 4 of the possible given choices, all 4 of the multiple choices had a unit of electron volts. So we need to divide this value by 1.6 times 10 to the negative 14. That is our answer in electron volts, which is 7.9 times 10 to the negative 1. Okay. Which is A. Yeah. A magnet is passed through a solenoid comprising 5 turns in a cross-sectional area of 0.6 meters squared. So we're given EMF, we're given N, which is 5, we're given area, which is 0.6. Calculate the EMF if the same magnet passes through another solenoid with 3 times as many turns and half the cross-sectional area at the same rate. If you halve the cross-sectional area, since area is proportional to EMF, it will halve EMF. However, turns, the number of turns is also proportional to EMF, so it will be 3 over 2. So the overall change to the EMF would be 3 over 2, basically. Like the multiplier. Actually, maybe I can just use the webcam for this. So 0.75 times 3 over 2. I'm not sure if that's very visible. Yikes. Okay. Second time. How many more times is it going to happen? I don't know. Hopefully it doesn't happen more times. But hopefully you can see that. It's 1.125. I don't know what happened. Okay, 1.1. It's B. Yeah. Black body at a temperature of 6040 Kelvin produces photons across a range of frequencies. Okay. Maximum number of photons is produced. I believe it's just this formula. 6,000. It's in Kelvin, so we don't need to change it. I actually haven't memorized the Wien's displacement constants. Okay. It's asking for frequency, but the formula uses wavelength. Okay, so what I'll do is my phone fell over sounds. Lambda max equals B over T, and B is, let me just say, 2.898 times 10 temperature of 6040. And it's in Kelvin, and that's the correct units we want. Okay, something to note, since the questions are asking for frequency and not lambda, not the wavelength, we can use the wave equation of light. So C equals F lambda, and then we can just rearrange for F. Well, in this case, we can rearrange for lambda. So C over F. So we solve that in. We get that. So we times by F on both sides. Alright, so gets rid of that. And we just divide by this. Yeah. Hopefully that makes sense. So 3 times 10. I mean, it should make more sense if I demonstrate on the calculator. So hopefully you can see what I mean by this. Okay, so here I just put the fraction of 2.898 times 10 to the negative 3 over 6004. That's the frequency. Okay. 6.25 times 10 to the 410. Yeah, that's A. Okay, Coulomb's law describes the observation that an electromotive force in a circuit may be induced. No. No, that's Faraday's law, pretty sure. Well, no, that's not Faraday's law. It's like an electromagnetic induction. Charged particles moving across magnetic fields experience force. I don't think. No, no, no. Like electric charges repel one another. Yeah, that seems like it. Yeah, it's D. C, by the way, seems more like Lenz's law, the opposition, like of the change in electromotive force. What is a consequence of symmetry in particle interactions? Um, C is incorrect. Antiparticles. So on Feynman diagrams, antiparticles are drawn with an arrow going backwards in time, but they're not traveling backwards in time. That's just the notation, I believe. Total mass of the particles will decrease. No, I don't think that's correct. So, in terms of the symmetry, charges on particles will always be different. I don't think so. It's just A, right? Like, yeah. Okay. Magnet moving through a coil of wire will induce a current with a magnetic field. Opposite in direction to the change in flux. Yeah. So that's related to Lenz's law, once again. An electron is best described as a lepton. It is a lepton with a larger mass than a positron. No. So an electron is a lepton, yeah. Positron is the antiparticle or anti-electron. It has an opposite charge and an opposite spin, but has the same mass. Yeah, so it's not A. It's not a baryon, so it's not B. A meson, again, involves quarks and is a type of baryon, so it's not C. So that just leaves D. Yeah. A particle whose interactions can be mediated by photons. Photons mediate the electromagnetic force. Electromagnetic force is experienced by charged particles. An electron is charged, so it's D. Two objects experience a gravitational force, F, between them. Calculate the magnitude of the force acting between the two objects if the distance between them was doubled and the mass of one object was doubled. If the distance was doubled and the mass was doubled, of one object was doubled. Okay. This is a good time to use this. Okay, so we have the force. G, gravitational constant times the mass of the mass, or the mass of an object times the mass of another, divided by the distance between two centers. Let's say we doubled one. Okay, so we just put a coefficient of 2 at the front, but we doubled the distance as well. And we need to put brackets around it to still represent that. The distance doubled. The value of the distance doubled, but we're subbing in the value into the formula. Let me just double check that. If the distance was doubled and the mass of one object was doubled, it's this. So, once you expand out the denominator, it becomes 4r squared. So then 2 cancels, leaving us with 2 in the denominator, which is basically just timesing a half. So the force actually halves based on the proportionality. So it's B. Yeah. Yeah, so far so good. We're going very slow though. That's probably one. A train is traveling at relativistic speed and is about to move through a tunnel. Okay, so immediately think about length contraction or just special relativity in general. An observer on the train measures the train and tunnel. What? A train is traveling at relativistic speed and is about to move through a tunnel. An observer on the train, so The observer is in an inertial frame of reference to the train, and they measure the train to be 95 meters, but also the tunnel to be 95 meters. The second observer is stationary relative to the tunnel. They would observe the train to simultaneously enter and exit the tunnel. Decrease its mass? Definitely not. Move faster while in the tunnel? I don't see why that would happen. No. Be shorter than the tunnel. Why? Because they're in a non-inertial frame of reference with this train, so they're measuring the dilated length, which is or the contracted length of the train. So I think it's D. Okay, it is. The half-life of an unstable subatomic particle is measured by a stationary detector to be longer when its velocity approaches the speed of light. It's experiencing time differently. Yeah. See. It's, time dilation because of the relativistic speeds. A 20-kilo object is placed on an inclined plane with a slope of 35 degrees if the object experiences a frictional force of 40 degrees and no additional applied force. What is the acceleration? Okay. I'm going to write the values down. Mass equals 20. Theta equals 35. Frictional force equals 40. Okay. Here we go. We're back. So we're going to draw a cute little diagram. So 35 degrees. That's the incline of the slope. Okay. There we go. The object is here, and that's its weight force. And we're going to draw a triangle that's parallel and perpendicular components. Here is actually 35 degrees as well. This angle, the top of the triangle. And we're experiencing a frictional force, so it's 40 newtons up. Okay, so we're going to ignore the vertical components because they're kind of relevant in this case in terms of the acceleration. So the parallel component here from the weight force is so force parallel, the net force parallel equals, let's say downwards is positive, upwards is negative. So it's mg sine 35 degrees, as the parallel component is the opposite side to the angle, and then the hypotenuse is the actual weight. So there we go, and minus 4 from it. Okay, so solve this, we put this into our calculator. The mass is 20 kilos. We need to convert the units. We can times it by 9.8. Sine 35 degrees. Make sure to check your degrees. Minus 40. So that's the net force. And using Newton's second law, F equals ma, we get that value. So 2.42. Obviously, around it just because I'm not going to write the entire number. Divided by its mass, which is 20. So we're going to use the exact figure. So then we get an acceleration of 3.6 meters per second squared. So again, it's two significant figures, which is A. And it is A. Okay. Calculate the electric field strength experienced at a distance of 2.8 times 10 to the negative 11 meters from the center of a helium nucleus. Okay, immediately we're thinking helium nucleus. It has 2 protons. And it's talking about the nucleus itself, not the entire atom, because if it was, then it would be neutral. So Yeah. Um, Protons have the same charge as electrons, but they're just positive. And the charge in coulombs is 1.6 times 10 to the negative 19, which are very. So we just make that positive. We just make this value positive for the protons. Okay. We find our formula for electric field strength. So just have that, and then we have the distance as well. Okay, so this 1/4 pi epsilon is 9 times 10 to the 9, which you see here, Coulomb's constant. Okay. I'm just going to change the screen again. So, E equals 4 pi epsilon naught q over r squared. That's the formula. We're trying to find electric field strength, so we don't need to rearrange the formula. We sub in the constant, which is 9 times 10 to the 9. The charge in this case is 2 protons, so we double the protons. The charge, so 2 times 1.6 is 3.2. So we write 3.2 times 10 to the negative 19. And then this is all divided by the radius, which is 2.8 times 10 to the negative 11, and this is squared. So we put that into our calculator. This does not seem right, but I think it is. I don't know. Is it? Yeah. Yeah, seems reasonable, I suppose. 7 times 10 to the 12. 7 times 10 to the 12. Okay, that is an answer. So let's see. Okay. Question 20, which is the last multiple choice question. Goodness me, it took quite a long time, okay, to get to this stage. Energy level diagram for a simple atom is shown. What transition is allowed for an electron that absorbs a photon with a frequency of 6.3 times 10 to the 14 hertz? Okay, 6.3. What is allowed? Let me just check again. What transition is there? So first we find out the energy of the photon. So we can use this formula. E equals hf. In this case, again, h is Planck's constant. Okay, so 6.626 times 10 to the negative 34 times, what was the frequency? 3 times 10 to the 14. Yeah. We solve that into our calculator. We get a value of 4.17438 times 10 to the 19. However, the energy level diagram has its energy in electron volts. So we need to divide this by 1.6 times 10 to the negative 19 to convert it into electron volts, which gives us a value of 2.61, which is 3 significant figures. So 2.61 electron volts. So we're going to plot that and see which transition kind of equals that. So if it absorbs it, once the electron goes back down the energy state. So once it goes from the higher energy state down to the lower stationary state, it's going to emit that photon again. Okay, so immediately we're seeing, the difference between the first and second stationary state or energy state is quite a lot. Okay, we don't even need to do the calculation. We know it's much more than 2.6. Okay, 2.61. Same with 3 to 2. That's like more than 7. 4 to 3, however, that seems reasonable because obviously negative 3.4 plus 6, the difference between that is 2.6, which is basically spot on. So it's 3 to 4, yeah, which is D. Yeah. Okay, short response questions. Okay, I don't like the describe or explain questions, but ooh, neither does my phone. Goodness me. Okay, just just wait a minute. I don't know why that keeps happening. To be honest, it's actually starting to bother me a bit. Like it's scaring me. I- I'm I'm scared. I'm frightened. Okay. Describe how the atomic model proposed by Bohr addresses the limitation singular what of Rutherford's model. Okay, so immediately we should be thinking why are there specific emission spectra of for elements, right? For hydrogen particularly, and that wasn't explained by Rutherford's model. I'm not going to write a response. I'm just going to verbally say it. So just the key points. So like obviously there's limitations like the unexplained emission and absorption spectra for like different elements, particularly hydrogen. Explained by Rutherford's model. Um, but there was also the death spiral. So like Rutherford's model suggested that electrons would just keep orbiting, but they would lose energy, right? And that was a problem. So it didn't make sense in terms of that. They would lose energy somewhere, and then they would just spiral closer and closer to the nucleus until they just collide with the nucleus. But we know that doesn't happen, so there's a discrepancy between the model and what actually happens, the observations. So then Bohr stated that the electrons exist in discrete quantized energy states or stationary states, which then kind of corrects the discrepancy that was proposed by Rutherford's model, in which now there is an explanation for why the electrons don't just spiral to their death. Obviously, you wouldn't write that in an exam, but you wouldn't. Oh, the tragic end of the electrons. It really tears to your eyes. Like you wouldn't write that. Maybe in English, but not in physics. Okay, and then because of the quantized stationary states, that also helps. That also explains the specific, I guess, fingerprints, right, of each element in which they have specific emission spectrum, and that's explained by, the electrons existing in discrete stationary states in which they can absorb or emit photons of specific wavelengths and frequencies to move between stationary states. Something like that. Okay, the Rutherford model. So this is the sample response. The Rutherford model provided evidence for the presence of electrons around. Oh, we need to describe it. I'll say I'm very confident. Okay. I don't think I really explained that. I did say Bohr's model kind of orbits the nucleus, but I kind of said that for like, I don't know. I said that for both. So, however, Rutherford's model was limited because it couldn't account for the stability of atoms, as electrons orbiting the nucleus would gradually lose energy and spiral into the nucleus. So I didn't say that. I did say that. The Bohr model addressed this by explaining the quantized nature of these orbits and how electrons within the same orbit possess the same discrete quantity of energy. I basically did say that, so I'd say I got 3 marks or 2 marks. Yeah, no wonder it was singular because you first describe uh, the specific, you know, atomic models from both physicists. Okay. Yeah, clearly describe and explain questions are a weakness for me, and I feel like that's kind of the general consensus. Actually, not really. Maybe, I don't know. Particles move at a rate. So calculation question. Okay, pretty good. Average speed. We're dealing with uniform circular motion here. Okay. Okay, so we're given. Sorry for that. We're given the frequency, right? Particles move at a rate of 1.3 times 10 to the 6 times per second. That's the frequency per second around a circular particle accelerator with a radius of 35 meters. Okay. Okay. Very simple. Very simple. It's just put into the formula. So we're trying to calculate the average speed. So we use this formula. V equals 2 pi r, which is the circumference of a circle, divided by the period. The period is just the inverse of the frequency. Right? The frequency. And I believe the frequency was 1.3 times 10 to the 6. And since we're dividing by period, but then it becomes like this. This becomes, you're basically just timesing by the frequency. Well, I explained that horribly. Goodness me. Wait, is this centimeters? Meters. What? Okay. That's not straight. Okay, so basically, your timesing hit by the frequency, just normal. So if we simplify that, 2 times 35 is 70. So 70 pi times 1.3 times 10 to the 6. That's the value. Let me just check. Sort of figures. Okay. So the average speed is 2.9 times 10 to the 8 meters per second. Yeah, that is exactly what I did. List the forces that can be experienced by leptons. They cannot experience strong nuclear force, but they can experience the weak nuclear force. Gravity. Yeah. Oh, I thought I had to list every single thing. But okay. Pretty simple 1 mark question. It's basically a multiple choice. Not really, obviously. Not really. So it isn't. Okay. A solenoid consisting of 1,240 turns is shown. The length, okay, so this, when we access the formula sheet, immediately we're given the length, but we're also given the turns. This is a solenoid. You should be thinking this. This formula right here, B equals, I'll write it down. B equals mu naught Ni. Lowercase n Why does this happen? I swear I'm not moving. I swear I'm not moving. Like, I'm being honest here. I'm being honest. Some things, like, forget about physics. You know, is my house haunted? Just kidding, just kidding. Don't worry. Okay. Okay. That was not a funny joke, I know. Okay. N actually represents the number of turns per meter. So we need to recognize that. Okay. So 1,240 over 40 centimeters. Okay, we need magnitude. It isn't going to break after this time. It might. There's a chance it might. Okay. N equals number of turns, which is 1,240 over 0.4, which is the length of the line. Okay. And then we just sub that in. So, if you can recall, it was 4 pi times 10 to the negative 7, and then we times that by the number of turns per meter, and then we times that by 0.5, which is current. So that's the value. Go down. I swear it's awful. I swear. The same turn on, and that usually means it's moving. So, okay. 1.9 1.9 times 10 to the negative 3. 1.9 times 10 to the negative 3. Okay, so that's the magnitude of the magnetic field. Direction. Okay, we're using our right hand rule again. So since on the diagram, the current first goes up on the right side. Ooh. In this case, it's actually the opposite, I'm pretty sure, for solenoids. So it's your curled fingers become the direction of the current, and then your thumb becomes the direction of the magnetic field for the solenoid. So in this case, current goes up, and then it goes over like this. So now it's like this. So my fingers curl this way. Both current and the magnetic field are going to the left. Yep. That is correct. I got them right. Okay, that's good. Wait, is it right? An observer who is stationary relative to a moving spaceship measures the velocity of the spaceship to be 2 times 10 to the... Wait, I just realized I'm at a decent pace. Oh, what? Oh, wow. That's actually surprising. Okay. An observer who is stationary relative to a moving spaceship measures the velocity of the spaceship to be 2 times 10 to the 8 meters per second. Okay. This is worded so weirdly. Like, the calculation is not difficult. Trust me. Okay, calculation, definitely not difficult. Okay, I don't think people struggle with calculations. It's more about the contextualization of the question. So it's the comprehension of the question for special relativity, more so than the actual difficulty of the calculations. An observer who is stationary relative to a moving spaceship. I'm assuming that means like they're in a non-inertial frame of reference. So let's say I'm this observer. The spaceship is moving. There we go. But the fact that they add who is stationary relative to all moving. No, no, no. But the fact that there's a velocity that's 2 times 10 to the 8 helps kind of distinguish what this is, like what the scenario actually is. Because otherwise, the velocity of the spaceship that they record is 0, right? If they're in the same inertial frame of reference as the spaceship, it's going to be 0. So we know that they're measuring um, velocity because they're not in the same inertial frame of reference. Okay. So we'll give them velocity, which is 2 times 10 to the 8, the length of the spaceship. So this is the dilated length. Okay. So we can access the form sheet. Dilated length is 18. So the proper length should be longer. That formula down. Yep. Okay, so the dilated length is capital L. The proper length is capital L subscript 0. So we sub it in, and then we divide by the square root thing. And then we have 2 times 10 to the 8 over 3 times 10 to the 8. And then this is all squared. And yeah, just below the capital. Okay. We can actually cancel these values out, so this simplifies things. Okay, square root of 1 minus 4 over 9. Yep. Like we predicted, it's a large value. Two significant figures, and we got 24 something. So that's yep. Okay. Making good progress here. Energy, electron volts of a photon, the wavelength of. This seems like a lot of marks for a very simple question to use. Okay. Wait, 5. Oh, I didn't change the screen. Oops. Okay. So here's the question I just read. So, first, the wavelength 405 nanometers. And then we need to give the answer to 3 significant figures. Okay. I'm just going to check. Okay. So we're using this one. E equals HF. We're given a wavelength, so we need to use the wave equation for. In this case, we're dealing with light, so velocity is just c, right, which is the speed of light. We rearrange for f, so f equals lambda over c. I mean c over lambda. I apologize. We sub in this value, or this equation, into that, so you get E equals, so for the messy, like organization, but yeah, HC over lambda. So here, this becomes 6.626 times 10 to the negative 34, and this is not messy because yeah, it is. The times 3 times 10 to the 8. This is all divided by 405 times 10 to the negative 9. 10 to the negative 9 is because it's in nanometers. If you forget your scientific notation or prefixes, it's in the sheet, so don't worry, don't panic. If you need double checking in a exam, feel free to um, just calmly check it, verify it. Ease your concerns. Okay. This should yield the energy of the photon in joules. But remember, the question specified it to be given in electron volts. So we need to do one more step, which is divide this value by 1.6 times 10 to the negative 19. This is very messy. I'm going to write this all just in one line of working. Just Planck's constant. And then speed of light, this is divided by 405 times 10 to the negative 9, because it's 405 meters, converting it into meters. And then we also divide it by 1.6 times 10 to the negative 19. It is because it's in the denominator already, and because of that, I just need to. So here you go. If you have a closer look, writing isn't superb, obviously, but yeah, hopefully it's legible somewhat. I mean, the calculator should hopefully be quite legible. That should be. That gives us 3.06. Oh, this is not good. This is something I need to revise. Significant figures. I don't know if the 0 counts as a significant figure here. I think it does. Yeah, I think it does. So it would be 3.07. Okay, I think it is. 3.07. That's in electron volts. Okay, it is. 3.07. Okay. I only have like a few questions to go. It's pretty surprising, to say the least. Given that I kind of had to explain some things here and there, but alright, whatever. A satellite orbits a planet of mass 6.42 times 10 to the 23 kilograms at a height of 5,000 kilometers. We need to convert that to meters from the surface. From the surface. That is not the value we put into the formula as R. The planet has a diameter of 6,780 kilometers. That is also not the value we use to add to the surface. We need to halve that first. So there's two things we can trip up on. The units, adding as well. We need to halve it to get the radius because it's measured from the center of the object. We're trying to find the speed, so we're using centripetal force here. So we're combining the gravity formula. So F equals G. Wait, are we? Wait. A satellite orbits a planet. No, we're using no, we are using that. Yeah. Okay. Let me just write down. I'll go to a brand new page. Okay. The mass of the planet. I'll use capital M. And then R r equals 5,000. So I'll convert to kilometers after I add the correct distances. 6780 divided by 2 times 1,000. So here's the mass, 6.42 times 10 to the 23. And then R is, in brackets, 5,000 plus 6,780 divided by 2, because that's the distance in kilometers. So then we multiply 1,000 to convert to meters. Okay, so half of this. So we can just put this in. I mean, we can put in the calculator, but I genuinely just could. I'm not sure why I'm not. That's the value in kilometers. We just times it by 1,000. We get 8,390,000 meters. Which makes sense. So now, what we'll do is, since we know that the force of gravity equals the centripetal force, we can demonstrate that by writing that F subscript G equals F subscript C to represent that equivalence between the force due to gravity being the centripetal force. And we can solve the values. So G capital M lowercase m divided by R squared equals mv squared over R. We know that m can cancel. Alright, they represent the same thing. If we square R, if we multiply by R squared on both sides, it removes it here, and it removes 1 here, but then it adds 1 here. Actually, no, well, we're not meant to do that. Okay, so first, okay, I'll demonstrate the working if this was a true exam. Okay, so I'll do this, then I'll do so I multiplied by R on both sides, so then I cancelled 1 with the last. So it's still left 1 in the denominator, but on this side I cancelled the R. Now there's nothing. We're trying to solve for speed. I think it's fine. We're square rooting both sides to calculate speed. Solving the values. So G equals the gravitational constant, which is 6.67 times 10 to the negative 11. We know the mass, it's given 6.42 times 10 to the 23, and we divide it by the radius, which is 8,390,000. That's all. That should be speed. Okay, so we can get a value of the speed of 2. What was the significant figures? 2 significant figures. 2.3 times 10 to the 3 meters per second. Yep. So the value was 2,259, rounded to the nearest value. Well, the speed was 2,259 rounded to the nearest value. But if it's in 2 significant figures, it's 2.3 times 10 to the 4. Okay, this is the last question for paper one. Okay. The Feynman diagram for a neutrino decaying into a proton and electron is shown. Okay. Describe the significance of the electron antineutrino in this particle interaction. It allows the interaction to obey the conservation of lepton numbers because, okay, you know what? I'll demonstrate why. So when the neutron, which is up, down, down, when it decays into a proton, which is up, down, it's a electron and an anti-electron neutrino. That is not heavy. Neutron, neutrino, and the minus disposal. Yep. So you can see on the left side, we only have a barrier, which is the neutron, obviously. So there's no leptons here. The lepton number on the left-hand side of this interaction is 0. We know that there's symmetry in particle interactions. So if the lepton number in the left-hand side is 0, then for the right-hand side it must also be 0 for the particle interaction to occur. If it doesn't obey the conservation of lepton number, it's not permitted. So since there is a lepton that is produced from the interaction, which is the electron, we need to get an anti-lepton. So to do that, we get the anti-electron neutrino. And because it's an antiparticle, for the lepton number, let's say lepton number, oops, I want to move. For the lepton number, it's like 1 minus 1. So it's 0, I believe that's how it works. And it's also 0 here, so that's conserved. So, the reason, the significance of the electron antineutrino relates also to not just the lepton number, but also the charge. So the conservation of charge, this charge symmetry. Here, in this case, you start out with a neutron. Neutron, is neutral, hence the name. Using it. You can also deduce that based on the charge of the quarks that it has, that the baryon has. It's lost to a third charge. The other quarks are negative for one third, so overall is 0. Since there's 2 down quarks and 1 up quark. Not positron. Proton is +1 because it has 2 up quarks and 1 down. So 2 times 2/3 is 4/3, minus 1/3 gives us +1. So charge on the left-hand side equals 0. This is +1. Electron, like the other leptons, so for muon and tau, they're all -1. So it's +1 minus 1, so that's 0. Bosons don't have a charge, they're just mediators of the forces. The reason why electron antineutrino is so important in this, because earlier, I was saying how the electron antineutrino is an anti-lepton, so it's an antiparticle, so that's why this interaction obeys the lepton number conservation law. But the significance of having the neutrino is that it doesn't actually contribute to the charge. And that's very important. Because otherwise, this, the charge on the right hand side would not be the same as the left hand side. Let's say we had a positron. Positron would be +1, meaning our right hand side would have a charge of +1. Left hand side has a charge of 0. Where does the +1 come from? It can't occur. So that's why interaction in that case would not be permitted. In this case, however, since this is a neutrino, it does not contribute to the charge. It's neutral, just like neutral, and so charge for the right hand side is also 0. And because that, it obeys the charge symmetry, meaning that this interaction is actually permitted, and that's why the neutrino in this case is so significant. Okay, so the law of conservation requires the baryon numbers and electron numbers to be conserved during the particle interaction. I think I'm correct, because although it asks for conservation, this is also, I'm pretty sure, conservation of charge as well. So that's the last question in paper 1. So I probably will be doing more videos. I'll probably get better at them, later on down the line. But that's all from me, I suppose. Yeah. I'll get better. I'll improve, I promise. But I suppose that's about it. Oh, I didn't even show the sample response. Well, here's the sample response. See, this is exactly why I need to improve. Exactly. I'll probably do other subjects as well. Maybe for chemistry, specialists, biology. Probably not English, because English doesn't have questions. It has past questions, but since it's a creative kind of subject, you can't really yeah. So I'll probably do videos on specialist methods, and then physics, biology, and chemistry. But yeah, that's all from me.